So in this video, we're going to extend our knowledge of how to calculate deflections using the unit load or virtual work method to help us calculate the reactions for a statically indeterminate beam structure. In this course, we're only dealing with beam structures. However, the concepts do apply also to frame structures. So we have a beam here with 3 vertical reactions and 1 horizontal reaction, and therefore there are too many unknown reactions for us to use statics alone to be able to calculate the reactions and then go on to draw our shear force and bending moment diagrams. So we need a way in which we can calculate one of the redundant reactions. So like we did with trusses, what we want to do is remove one of the redundancies, and so we can have a primary structure and redundant structure that are equivalent to this indeterminate structure. And we could remove any one of these redundant supports, but for this example, or this explanation, I'm going to remove the redundant support at B. So the concept is, if we had the original structure, so we had RAY, RAX, we have the real load P, a reaction RBY, and a reaction RCY. We're saying that will be equivalent to 2 structures, statically determinate structures. So now we have we still have reactions at A. I'll call this dash because it's slightly different. We still have the real load, and we still have reaction forces RCY at the right hand side, but we no longer have the redundant support at B. I'll just draw B on there for the moment. But if we were to add to this structure another structure, so we still have a vertical reaction RAY, let's call this dash dash because it's different again, RAX dash dash, and RCY dash dash, plus some force RBY, the real reaction in the original structure we considered, that would get rid of the displacement. So in this primary structure, we would get a displacement delta B, but in the original structure, we know we have 0 displacement at B. So if we can apply just enough force back at B to get rid of this displacement delta B, we will have recovered the original structure. So we're going to work through the procedure for calculating the structure. We're not going to actually write any bending moment equations, but we will show the procedure that we would use. So with our primary structure, we want to calculate the deflection delta B that would happen due to the force P. So let's draw that. So we have the primary structure, which still has the pin support at A, still has the roller support at C, still has the real force at P. And as a result of applying this, we can calculate let's draw it a bit better than that. We can calculate the bending moment due to this force. And this bending moment we're going to call capital M. What we'd like to know though is what the displacement, the fictitious displacement delta B would be as a result of calculating. As a result of applying load P but removing the redundant support. So we have exactly the same structure, exactly the same boundary conditions, but to calculate the displacement, remember from the previous section of work, if we apply a unit load, I'm applying it down, could just as easily apply it upwards, I will get a deflection of the structure, and as a result, the deflection of the structure down to a unit load will be called delta BB dash. And what we'd like to know is how much I'd like to factor up this load so that I get no displacement there. But before that, we need to calculate delta B. So as a result of applying this unit load, we'll get a bending moment diagram. And this bending moment diagram now for the unit load will be called little m. So from there, from these two structures, we can then calculate the deflection delta B. So let's go with delta B. So delta B equal to the integral between 0 and L of m over EI, all integrated over dx. The second part of the procedure will be to calculate the flexibility coefficient. And similar to what we did with truss structures, we wish to know, again, we have the same geometry, the same boundary conditions, and if we apply a unit load where we'd like to know the flexibility coefficient and in the direction that we'd like to know the coefficient, from this arrangement we will get a bending moment diagram like this. So, and again, this is m, and this is identical to the little m we've already calculated in calculating the fictitious displacement delta B, and very similar to how we calculated flexibility coefficients for trusses, we can say that our flexibility coefficient, so FBB, is equal to the integral between 0 and L of little m over EI, all integrated over dx. So if you cast your mind back, that isn't that dissimilar from what we had for trusses, where we had a summation for displacements. We had, so delta equals the summation of NN over NNL over AE. For beams, and then for the flexibility for trusses, we had the summation of little n L divided by AE. And so for beams we have very similar now, that the delta equals integral between 0 and L of m over EI dx, and the flexibility coefficient is equal to the integral between 0 and L of little m over EI dx. So with our flexibility coefficient calculated, our fictitious displacement delta BB, which we don't wish to know, or we wish to get rid of, because in the real structure we have no displacement at B, we can set up our compatibility equation. So writing that concept down, but we don't want a displacement at B, we write our compatibility equation. And so in this case we're saying that if we have the fictitious displacement delta B that only occurs in the primary structure but not in the real structure, we wish to get rid of this by multiplying our flexibility coefficient by a number. So this is for a unit load, so we want to multiply it by a real load that will eventually get us to 0, and then this real load is actually the real reaction RBY that occurs in the real structure. So this is the structure right back at the start, and so is this reaction force here RBY. Okay, so at this point, using our compatibility equation, we can now finally know our reaction RBY. In the meantime, we've had reaction forces for the redundant system, and we've had reaction forces for the primary system. So we have reactions that were calculated at A, at the left-hand side, and at C on the right-hand side. But these are not correct because we never considered this reaction force RBY. So now, with knowing RBY, we can finally calculate our real reactions. And to do that, we go all the way back to our original structure. And so we have RAY, which is unknown. We'd have RAX as well, but we don't have anything in the X direction. We have an RCY, which is unknown. We have the real load P, which we do know. And we also have RBY. So we know P and we know RBY. And if we use these, just consider them as external loads, we have enough equations of equilibrium so that we can evaluate RAY and RCY. And once we know those values, we can rewrite bending moment functions and shear functions to draw our bending moment and shear force diagrams for this structure. In the next video, we're going to go through a worked example of how exactly we do this with every calculation step along the way. But that was really an idea of the concept that we're going to be applying.